Hi guys, we're back with the next topic in Trig. So topic 1 and 2 were kind of grouped together. It was the introduction to compound angled identities and then applying them in exam type questions. And now topic 3 is double angle identities. And we kind of had an introduction to this idea in our previous lesson, but now we're going to look at our last two identities. So in the first lesson, in topic 1, we learned 4 new compound identities, which are on your formula sheet. This is now the next two identities that are also on your formula sheet, and they're the double angle identities, very commonly asked, and so a really important topic. So let's dive straight into identity 1, which is cos of 2 theta. Now, I actually did this one in the previous video, because what we're going to do is we're going to rewrite 2 theta as theta plus theta, and then we're going to use the compound angle identity. And the compound angle identity says that you cos the first angle, cos the second angle, and this identity then says you subtract sine the first angle, sine the second angle. And so this actually becomes cos squared theta minus sine squared theta. And that is the first identity for this. There are actually 3 identities, but that's the first one. I'll summarize them in a moment. Now that's on your formula sheet. Cos 2 theta is cos squared theta minus sine squared theta. Now the reality is that we can keep morphing this into something else, because you will remember, and I mentioned this in the previous example, in the previous video, that cos squared plus sine squared equals 1. And so if you want to replace, for example, cos squared, you can write cos squared theta as 1 minus sine squared theta, and vice versa. You can rewrite sine squared theta as 1 minus cos squared theta. So there's actually 2 ways that we can morph this. The first way we can morph this is by taking out the cos squared and writing 1 minus sine squared theta. So that's replacing this cos squared, then minus another sine squared theta, which would equal to 1 minus 2 sine squared theta. So this is the second way that cos 2 theta can be rewritten. So that's almost like a second identity within this first identity. And then a third way you could have morphed this is from this line. You could have replaced the sine squared. So you could have said it's cos squared minus 1 minus cos squared. So then that actually becomes minus 1 but plus cos squared. So it actually becomes 2 cos squared theta minus 1. And this is the third kind of identity within this identity. So actually cos 2 theta can be rewritten in 3 different ways, and so when we do identities and equations, we're going to use all of these different ways. So what's given to you on the formula sheet is that cos of 2 theta can be rewritten as 3 identities. It's either cos squared theta minus sine squared theta, which is very close to this identity of 1. So just be careful. If it's a plus, it's 1, but if it's cos squared minus sine squared, it's actually cos 2 theta. Or it can be rewritten as 1 minus 2 sine squared theta, or it can be rewritten as 2 cos squared theta minus 1. Fortunately, given to you on your formula sheet, and so you don't have to remember them, they can ask you to derive it. Now, it's not particularly difficult to derive, so I wouldn't remember it off by heart. You just have to remember to rewrite 2 theta as theta plus theta, and then kind of just apply the identity. So that's our cos double angle. We'll use them in a moment and kind of see how this plays out in questions. And our second identity is sine of 2 theta, which we haven't actually looked at yet. It's the same concept in that you change 2 theta to theta plus theta, and then you use the identity, the compound angle identity, which is sine the first angle, cos the second angle, plus cos the first angle, sine the second angle. Now those are actually identical terms, and this is just swapped around. So if you swap it around, you get 2 sine theta cos theta. Now it only has one version. There's no way to kind of morph that because there's no sine squared or cos squared, and so it only has one identity, also given to you on your formula sheet. Now those are the end of the new identities from a trick. So the new identities from a trick are the compound angle ones, of which there were 4, and then these 2 new ones. So let's go and have a look at how questions can look. So what I've done here in example 1 is, in the box, I've just written the identity that we should kind of be flagging in our head when we see this pattern. So it says write the following as a single trig ratio. And you do get so used to this. Once you've practiced enough and you've done enough past papers, you just see this pattern and you realize what it is straight away. So 2 sine 3 theta cos 3 theta is exactly that pattern there. So what they're saying to you is that here that A is actually 3 theta. So this is going to collapse to sine 2 times 3 theta. So this is sine of 6 theta. Now notice lots of people think that double angle identities only apply to like 2A or 2 theta. This is double anything. So for example, 6 theta is double 3 theta. And so it is a double angle. Anything can actually be a double angle because you can always halve something. So just to note here that, just to say this again, it fit the pattern and that A is 3 theta. And so that A was 3 theta, and so this collapsed to sine of 6 theta. Okay, let's look at the next one. 4 cos x sine x. Okay, well, first of all, it doesn't look right because it's in the wrong order, but multiplication is commutative, so I probably wouldn't bother writing that. Now, 2 sine of the same angle, cos of the same angle. What really should flag a red flag in your head is when you have sine of an angle multiplied by cos of the same angle, you should really think double angle identity. It doesn't really matter what that coefficient is, because basically, can I rewrite this with a 2 sine x cos x? Because 2 sine x cos x will collapse to sine of 2x simply by looking at my identity. Now, can I write it like that? Absolutely. I would just need a 2 there, because 2 times 2 would give you a 4. So this actually collapses to 2 sine 2x. Okay, on to the next one. Anything with cos squared minus sine squared, you start to realize that that's a cos double angle identity. So 2 theta here is actually what's represented by A in my identity. So it's going to collapse to cos of 2 times 2 theta, which is cos of 4 theta. I've always suggested making a little cardboard kind of note that you always have with you when you're doing trig with the compound angle identities on, and I would definitely add all these double angle identities. It helps a lot. I go on to the next one. 1 minus 2 sine squared. Again, you start to recognize those patterns. This is exactly the same pattern as this version of cos 2a. Now in this case, this is 4x. So 4x represents what a is. So this is going to be cos of double 4x, which is going to be cos of 8x. Okay, so you start to pick up these patterns eventually. Okay, let's look at the second example. How can we do this involving numbers and not only letters? So this question says 2 sine 15 cos 15. Perfect. Hopefully you see cos of an angle and sine of an angle and you think double angles, because clearly 15 degrees is A. So this will collapse to sine 2 times 15. Now, of course, I wouldn't show that in an exam. I wouldn't bother. But basically, this is sine of 30 degrees. And sine of 30 degrees is a half. Right, on to the next one. I see cos 15 plus sine 15 all squared. So I'm going to multiply that out. I probably should be using my cheat of how I multiply it out. But just in case, I'm actually going to write out the binomial times the binomial, which is cos squared 15. And then you get cos 15 times sine 15 and cos 15 times sine 15, so 2. Now I'm going to write sine 15 first simply because I know this pattern. Sine 15 cos 15 is a double angle pattern. And then plus sine squared 15 for my last term. Now what's going to happen here is that cos squared 15 plus sine squared 15 will give me 1. And this 2 sine 15 cos 15 is actually exactly what I did in the previous question. So that's actually plus sine of 2 times 15 using this sine double angle identity, which I'd written up there. So that's 1 plus sine of 30, which I know is a half. So it's 1 plus a half, which is 1 and a half. Or you could write 3 over 2 or 1 comma 5. Just don't, please don't make the mistake of distributing the power of 2, because it's a binomial times a binomial. So it's quite a good exam question because it tests your sine squared plus cos squared identity and your double angles, which is quite nice. Okay, on to a couple more. Next question says 2 cos squared 22.5 minus 1. You get very used to that, but 2 cos squared minus 1, and I immediately think cos double angle. So here 22.5 is the A value, so it's cos double 22.5. And double 22.5, you also get used to these kind of values because they come up a lot, because double 22.5 is 45. And cos of 45 is root 2 over 2. Right, question D. Question D says sine 165, cos 165. And the moment you see sine of an angle and then cos of an angle, you should think double angles. So basically, if this was 2 sine 165 times cos 165, that would fit a double angle identity. So this would be sine of double 165 degrees, which would be sine of 330, I think. Now the only problem is there was no 2. There's no 2 there. So you can't just suddenly pop in a 2 because you felt like it. That coefficient was 1. So if you're going to put in a 2 to make this work for yourself, you have to undo the fact that you've now suddenly introduced a 2. And if you've suddenly multiplied by 2, you also have to basically divide by 2. So hopefully you'll agree with me that a half times 2 is 1. So by introducing the 2, because I needed it there, I've now undone the 2 being there. And so basically it's a half times sine of that, which is a half times sine of 330. Now sine of 330, if I do reduction, because it's said without a calculator, that's negative because it's in the fourth quadrant, sine 30. So just quick recap of reduction, because we haven't done reduction in forever, is don't forget you rewrite the angle using an axis minus, in this case, 30 degrees. And then your first question is, what quadrant are you in? Because that will dictate the sign, as in SIGN. So this is in quadrant 4. And so sine is negative. Don't forget your all stations to Cape Town diagram. And then if you're working off 360, your name doesn't change. So it's sine 30. And sine 30 is a half. So I get a half times negative a half, which is negative a quarter. Now the great thing is you can always just plonk that question into your calculator, and hopefully it gives you that same answer, because then you immediately know you're right. Right, let's have a look at the next one. Question E, 1 minus 2 sine squared. Again, you start to get used to that pattern. That's a cos double angle. And in this case, 105 is A. So this will become cos of 2 times 105 degrees, which is cos of 210 degrees. Now again, I'm going to do reduction. I prefer to work off 180 degrees rather than 270, because then the name stays the same. So I ask myself, first question, what quadrant is that in? Quadrant. That'll be 180 plus 30, so that's quadrant 3. So cos is negative, and you're working off 180, so your name stays cos. So it's negative root 3 over 2. Again, you just plunk that in your calculator, and you know very quickly if you're right or wrong, which is really comforting in an exam. Right, let's look at example 3. Now, these are really good exam type questions, example 3. It says simplify the following. Now, these type of reduction questions, we've always kind of been able to get them down to, special angles, and then you use the special angle ratios, and then they simplify, which is great. Now, in this case, you'll notice that you have sine of 40. Now, 40 is not a special angle. And if I rewrite it as 90 minus 50, 50 is not a special angle. If I look at the bottom, I don't see anything that, 100 can't be rewritten using an axis and 40. Try to only use compound angle identities when you are desperate, absolutely desperate. So first look for double angle identities. Now that is a double angle identity, because 2 sine 40 cos 40, the moment you see sine of an angle times cos of an angle, you should think double angle identity, even if the 2 isn't there, because don't forget you can always put it in there. So this would be equal to sine 2 times 40, which will be sine of 80. Now why will that help me? Because sine of 100, I can rewrite 100 as 180 minus 80, which means I could get them to matching angles. So first of all, I want this top to have a 2 in it, but as we said in the previous examples, you can't just suddenly have a 2 because you felt like it. And so if you want to introduce a 2, you've got to have the fact that a half of 2 would keep the coefficient of 1, which it actually was. Now, because I've kind of glimpsed into where I'm going to rewrite 100 as 180 degrees minus 80. So now this top becomes a half, and if I just circle it in green, that becomes my sine of 80, my double angle. So that's sine of 80 in the numerator. Over. Now, first question is quadrant. 180 minus 80. Well, if you're working off 180, you're quadrant 2, and sine is positive in quadrant 2. And if I'm working off 180, my name stays the same. So my sine of 80 cancels my sine of 80, and I get a half. Now, the most important thing is please only ever use compound angles when you're desperate, because a compound angle identity makes it very, very complicated. You know, there's 2 terms and you're multiplying stuff, whereas your double angle identities make something nice and small. Right, let's have a look at B. This is also an exceptionally good exam type question. Without a calculator, let's simplify tan of 15 plus cos 15 over sine 15. Now, if I'm ever asked to do anything and I see tan, I don't know anything about tan. There's no compound angle identities with tan. Well, there are, we just don't study them. There's no double angle identities that we study with tan. And so immediately I see tan, I always change tan to sine over cos. Now, that's an identity which we should know from grade 11. Now, when we get to identities, we will use that a lot. So let me just write it down on the side. Should be something you're familiar with. Tan of any angle is sine over cos. Now, how does that help me? Well, it doesn't really help me much yet, but now I've got 2 fractions. And one of the things, again, that we're going to discuss in identities is that when you have 2 fractions, always try and look for an LCD and combine them to 1 fraction. So my LCD here would be these 2 multiplied together. Now I'm deliberately going to write sine 15 first times cos 15, simply because I'm thinking double angle identities. And yes, that's missing the 2, but we've done that before. That's not a problem. That's going to be something about double 30. Now at the top, what I've done here is this has been multiplied by sine 15 to create the LCD. So this has been multiplied by sine 15. Sorry, that does say sine 15. So at the top, I actually get sine squared 15 in the first term. This has been multiplied by cos 15 degrees to get the denominator. So I must multiply the top by cos 15 degrees. And what do you know? At the top, you get sine squared of an angle plus cos squared of an angle, which is always 1. Did I say cos squared or sine squared? I don't know. Apologies if I made a mistake. Okay, now the bottom, I want to change into 2 sine 15 cos 15, because I've seen this kind of trick before. You'll notice it comes up a lot. However, you can't suddenly introduce a 2, which means I have to have a half. So now this 2 sine 15 cos 15 is actually sine of double 15, which is sine of 30. And I still have my half. Now sine of 30, I'm running out of space here, but sine of 30 is a half. So I have a half times a half at the bottom. So I've run out of space. So that equals 1 over a quarter. And 1 divided by a quarter, if I have a cake and I divide it into quarters, how many pieces do I have? I would have 4. I could use my calculator. So that's a really, really wonderful exam question. Great, let's move on to our last example. And this last example is I'm trying to bring in the Pythagoras type idea type question every time, because it's a very commonly asked question that we did from grade 11. So remember, with Pythagoras type questions, they give you one set of information first. So I know that tan is positive, which means I am not working in quadrant 4 and I'm not working in quadrant 2. But I also am told that theta has to be bigger than 180 and less than 360. So somewhere here. So can't be there, which leaves me with one option. This theta that they speak of, which I should have written here without a calculator, which I'll go and add in now. But that theta must be into the 3rd quadrant. Now, why do we do this? We do this so you can tell me the signs of x, y, and r. So the sine of x in this quadrant would be negative. The sine of y in this quadrant would be negative. And the radius is always the distance, so that's positive. So now I go and look at my definition of tan. Tan by definition is y over x. So this must be negative 3 and negative 4. Now notice it doesn't say negative 3 over negative 4, and so most people forget about the signs. So both of these are actually negative, which is why they simplify to a positive tan ratio. Now we should know our Pythagorean triple. Don't forget to always write Pythagoras in brackets. But r is 5 using Pythagoras' theorem. And once you have x, y, and r, you can do anything. So let's have a look at our first question. Our first question says, what is sine of 2 theta? Well, there's an identity for that. It's 2 sine theta times cos theta, because I don't know anything about 2 theta, but I know everything about theta. So sine of theta would be y over r, and cos of theta would be x over r. So this becomes over 25. That's actually positive, and I think it's 24 over 25. Now I should have said without a calculator. I'm really going to go change that in this question. So please note, you're not actually ever going to find theta, because the question will say without a calculator. If it didn't, I'd just find the value of theta using my calculator, and then this whole question is very easy. So what's cos 2 theta? Well, there's 3 ways to find out cos 2 theta. It really doesn't matter. I could use cos squared minus sine squared. I could use 1 minus sine squared. I could use 1 minus 2 sine squared, or I could use 2 cos squared minus 1. Now, I actually tend to use the one with only one of the ratios, simply because then I'm only working with one thing that I have to substitute, but it actually doesn't matter. You would get the same answer. So cos is negative 4 over 5, and I'm squaring it. So if I go simplify that, that's 16 over 25, which actually gets me to 32 over 25, minus 1, which is 7 over 25, I think. Great. Okay, our last question is tan of 2 theta. Now that's really nice, because tan, I don't have a double angle identity for tan. There is one, but we don't study it. But tan of 2 theta is great, because we do know another identity which can help us, which is the fact that tan is sine over cos. So if it's tan 2 theta, then it's sine 2 theta over cos 2 theta. Now I've already worked out sine 2 theta. It is 24 over 25. And now I'm dividing by, and cos 2 theta is 7 over 25. So you can tip and times, if they said without a calculator. So times by 25 over 7. My 25's cancel, and I get 24 over 7, which doesn't simplify, and so I leave it exactly like that. Great, so that's this video, basically on introducing these 2 new identities, although there's actually 3 identities within the cos double angle, and then just a couple of exam type questions of where double angles come up. They come up a lot, and so it's definitely one worth practicing. Okay, well done.